Welcome to Hydrodynamics, the study of liquids in motion. Across this three-part series, we will move from how a liquid flows, through the energies it carries, into the friction between its layers, and finally to what happens when a small body falls through it. We will say liquid throughout, but the same ideas apply to any incompressible, viscous fluid unless we say otherwise. The aim is a clear mental picture, not a wall of equations to memorize. Before we touch an equation, here is what you should be able to do by the end of these three decks. You should be able to tell streamlined flow from turbulent flow and place a flow in the right regime using the Reynolds number. You should be able to apply the equation of continuity to a pipe of changing cross-section. You should be able to state Bernoulli's theorem in two equivalent forms and use it on everyday situations. You should be able to compute the velocity of efflux and the range of a jet from Torricelli's theorem. You should be able to define viscosity mathematically and quote Poiseuille's formula. And you should be able to use Stokes' law and the terminal velocity formula for a falling sphere. Now, a moving liquid can behave in three distinctly different ways, and the differences are not in the liquid itself, but in how it is moving. In streamlined flow, each particle follows the same path as the particle before it, and streamlines never cross. Where streamlines crowd together, the liquid moves faster. Where they spread apart, it moves slower. Laminar flow is the steady flow of a liquid over a horizontal surface in layers of different velocities, and the word laminar is used almost interchangeably with streamline. Turbulent flow is disordered, with eddies and swirls, and it appears when the liquid moves faster than its critical velocity. Most of the input energy in turbulent flow goes into making eddies. Only a small part drives the liquid forward. To decide which regime a flow is in, we need one dimensionless number that compares the two competing influences inside a moving liquid. Inertia keeps motion going, viscosity damps it. The Reynolds number is the ratio of inertial force per unit area to viscous force per unit area. It equals the critical velocity times the density times the radius of the pipe, divided by the coefficient of viscosity. It is a pure number, no units, no dimensions. For pure water in a cylindrical pipe, it sits around 1,000. Below 2,000, the flow is streamline. Between 2,000 and 3,000, the flow is variable, neither fully streamlined nor fully turbulent. Above 3,000, the flow is turbulent. One quick trap. These thresholds are practical engineering guides for water in cylindrical pipes. The same liquid in a different geometry can transition at a different value of K. Now imagine a non-uniform pipe carrying liquid in streamlined flow. Liquid is neither created nor destroyed inside the pipe, so the amount of liquid crossing any cross-section per second must be the same. If a cross-section narrows, the liquid must speed up to keep the same volume rate flowing through. That gives the equation of continuity. The area at section 1 times its speed equals the area at section 2 times its speed, so the product of area and velocity is constant along the pipe, and area is inversely proportional to velocity. You can see this as a curve where velocity is high when area is small and falls smoothly as area grows. In a converging pipe, the area shrinks from a 1 at P to a 2 at Q, and the velocity grows from V1 to V2, with the product holding at every cross-section. A falling stream of water from a tap narrows as it falls because gravity speeds it up, and continuity says the area must shrink in inverse proportion. Deep water in a wide tank or lake looks still, not because it is calm inside, but because the cross-section is so large that any drift has only a tiny velocity by continuity. Continuity is not about forces, it is about counting. The shape of the pipe decides how fast the liquid has to move. That brings us to the end of the first deck. Three regimes, streamlined, laminar, and turbulent. The Reynolds number K equals Vc rho r over eta, a pure number. Continuity. A1V1 equals a 2V2, so an incompressible liquid carries the same volume rate through every cross-section. Once we know how fast a liquid is moving in each part of a pipe, we can ask how much energy it has there, and that is the subject of the next deck. Thanks for learning with Viscosity. A moving liquid can do work, drive a turbine, push against a wall, raise its own level in a tube. Where does that capacity come from? It comes in three forms, all measured per unit mass or per unit volume of the liquid. There is pressure energy, kinetic energy, and potential energy. Per unit mass, the 3 are P over rho 1/2 V squared, and GH per unit volume, the 3 are P itself, 1/2 rho V squared and rho GH. Notice that the per unit volume form of pressure energy is just the pressure itself. Pressure has the same units as energy per unit volume, because moving a surface by an infinitesimal amount does P times dV of work. The kinetic term 1/2 rho V squared will reappear shortly as the dynamic pressure. The potential term ρgh is the gravitational energy density. Keep those three numbers in mind because the next slide adds them up. Bernoulli's principle states that for an ideal liquid, one that is non-viscous, incompressible, and flowing in a streamline, the total energy per unit volume remains constant at every cross-section. In its core energy density form, the equation is written as P plus half rho v squared plus rho gh equals a constant. If we divide each term by rho g, we get the head form. P over rho g plus v squared over 2g plus h equals a constant. This representation is often more convenient because the terms, the pressure head, the velocity head, and the gravitational head can be conceptualized as physical heights. Each term corresponds to a type of energy density. The pressure term, P, represents the static pressure or the work pressure can do per unit volume. The kinetic term, half rho v squared, represents the dynamic pressure, and rho gh represents the potential energy density. Along a streamline, these terms balance one another. Where one rises, the others must fall. For the special case of a horizontal pipe where height is constant, the equation simplifies to P plus half rho v squared equals a constant. This means that where the fluid velocity increases, the dynamic pressure rises and the static pressure falls. Conversely, where the fluid slows down, the static pressure rises. This fundamental pressure trade-off is the engine behind Venturimeters, carburetors, and aeroplane wings. Every Bernoulli effect we are about to list shares the same mechanism. High speed, low pressure, low speed, high pressure. In an atomizer, paint gun, scent sprayer, insect sprayer, Bunsen burner, gas burner, oil stove, or exhaust pump, air is blown at high speed across a tube, dropping the pressure at the tube mouth and sucking liquid or gas up into the stream. On an aeroplane wing, air over the curved upper surface moves faster than air beneath, so pressure above is lower than pressure below, producing lift. In the Magnus effect, a spinning ball drags air faster on one side and slower on the other, curving its path. During a windstorm, fast wind over a roof lowers the pressure above, and pressure inside the house pushes the roof up. Two closely parallel moving boats attract each other because water between them moves faster than the water outside, so it has lower pressure, and the higher outside pressure pushes them together. Bernoulli also helps explain pressure variations as blood accelerates through narrowings in arteries. One mechanism, many faces. A Venturimeter measures the rate of flow of liquid through a pipe. It uses a horizontal pipe with a deliberate constriction and two vertical standpipes that reveal the local pressure. At the wider cross-section A1, the flow is slower and the pressure is higher, so the liquid in the standpipe sits higher. At the narrower cross-section A2, the flow is faster and the pressure is lower, so the standpipe level is lower. The difference between the two liquid columns is H, applying Bernoulli across the two cross-sections. And using continuity to write A1 V1 equals A2 V2 equals V, the rate of flow works out to V equals A1 A2 times the square root of 2GH over A1 squared minus A2 squared, where A1 and A2 are the cross-sectional areas at the wider and narrower parts. A larger H means faster flow. The pressure drop between the two sections is proportional to the speed squared. Now take a tank filled with liquid to height H, open at the top, and pierce a small hole at depth H below the free surface. The liquid spurts out horizontally with some velocity of efflux v, then falls under gravity in a parabola, landing at horizontal distance s from the base. Applying Bernoulli between the free surface, where the velocity is essentially zero and the pressure is atmospheric, and the jet just outside the hole gives the velocity of efflux as v equals the square root of 2gh. Notice something elegant. That is exactly the speed a body would acquire falling freely through the same vertical distance h the jet leaves horizontally from depth h. So it must fall a vertical distance h minus h before hitting the ground, and the time of flight is the square root of 2 times h minus h over g. Combining the speed and the time gives the horizontal range. S equals the square root of 4h times h minus h. The product h times h minus h is maximized when h equals h over 2, and the maximum range equals h, the height of the liquid column, when the hole is exactly halfway down. If instead the hole sits at the bottom of the tank, then h equals h, and the time required to empty the tank is t equals a over a naught times the square root of 2h over g, whereas the cross-sectional area of the container and a naught is the area of the orifice. The volume rate through the hole at any instant is v equals v times a naught, which equals a naught times the square root of 2gh, largest when the tank is full and falling to zero as the level approaches the hole. That closes the second deck. A moving liquid carries pressure, kinetic, and potential energy per unit volume. Bernoulli's theorem says their sum is constant along a streamline of an ideal liquid. In horizontal flow, Faster flow means lower static pressure, the engine behind Venturimeters, atomizers, and lift. The Venturimeter rate formula reads V equals a 1 a 2 times the square root of 2gh over a 1 squared minus a 2 squared. Torricelli's theorem gives efflux velocity V equals the square root of 2gh, and horizontal range S equals the square root of 4h times h minus h, maximized at h equals h over 2. One trap to keep in mind, Bernoulli applies to an ideal liquid, which is non-viscous, incompressible, and irrotational. Real liquids have viscosity, and that is the subject of the next deck. Thanks for learning with Viscribe. This is where the ideal liquid theory starts to break down. Bernoulli's theorem assumes a frictionless, non-viscous liquid. Real liquids are not frictionless. When one layer slides over another, the slower layer drags the faster one back, and the faster one drags the slower one forward. This internal friction is called viscosity, and the force it produces between adjacent layers is the viscous force, an intermolecular force acting between molecules in layers moving at different velocities. Take a layer of area A moving with velocity v, and a neighboring layer a small distance d. X away moving at v plus dv, the viscous force between them is F equals minus eta times dv over dx. The negative sign matters. It tells us the force on the faster layer is backwards, and on the slower layer is forwards. Friction always opposes relative motion. Rearranging gives the coefficient of viscosity as eta equals minus F over a times dv over dx, where dv over dx is the velocity gradient between layers. The SI unit is Newton-second per square meter, also called the Pascal second, and historically the decapes. The dimensional formula is ml to the minus 1t to the minus 1. Physically, the source of viscosity is different in liquids and gases. In liquids, viscosity comes mainly from cohesive forces between molecules. In gases, it comes from molecular diffusion. Faster molecules cross between layers and drag their momentum with them. Those two mechanisms give opposite temperature behaviors. For liquids, viscosity decreases with temperature. The empirical form is eta T equals eta naught over 1 plus alpha T plus beta T squared, where eta naught and eta T are the viscosities at 0 degrees and T degrees, and alpha and beta are constants. Hot oil flows more easily than cold oil. Useful knowledge when choosing a lubricant. For gases, viscosity increases with temperature, scaling as eta proportional to the square root of T, because heating a gas speeds up its molecules and increases the rate of diffusion across layers. For pressure, the viscosity of most liquids increases with pressure, but water is anomalous and decreases. The viscosity of gases is largely insensitive to pressure at moderate values. For steady, laminar flow of a liquid through a horizontal pipe of radius r and length L, the volumetric flow rate Q equals pi over 8 times p r to the fourth over eta L, where p is the pressure difference between the two ends of the tube. This is Poiseuille's formula. Notice how steep the dependence on radius is. The flow rate scales as r to the fourth, so having the radius cuts Q to 1/16 of its original value. That is why a small constriction in a pipe or an artery has such a large effect on flow, and why Poiseuille's formula is central to hemodynamics. We can rewrite the formula as Q equals P over R, where R equals 8 eta L over pi R to the fourth. R is the liquid resistance of the tube. This form deliberately mirrors Ohm's law. Pressure plays the role of voltage, flow rate plays the role of current, and R plays the role of resistance. Series and parallel combinations of tubes follow the same rules as electrical resistors, which makes life much easier. When two tubes are joined end to end, they are in series, and the same flow rate Q must pass through both because the liquid has nowhere else to go. The diagram shows 3 nodes. The inlet at pressure P1, the middle junction at P2, and the outlet at P3. The drop across tube 1 is P1 minus P2. The drop across tube 2 is P2 minus P3. The total pressure drop across the whole series is P1 minus P3, which equals the drop across tube 1 plus the drop across tube 2. Apply Q equals delta P over R to each tube and add the drops. The equivalent liquid resistance is R equals R1 plus R2. When two tubes share both ends, they are in parallel, and the same pressure difference appears across each. The total flow splits between them, so Q equals Q1 plus Q2, and the equivalent liquid resistance satisfies 1 over R equals 1 over R1 plus 1 over R2. Parallel paths always lower the overall resistance, because adding a second tube never hurts the flow. When a small spherical body falls through a long liquid column, after a short time it reaches a constant speed. At that constant speed, called the terminal velocity, the viscous force on the sphere is F equals 6 pi eta RV. This is Stokes' law. Here r is the radius of the sphere, v is its terminal velocity, and eta is the coefficient of viscosity of the liquid. A quick note on validity. Stokes' law is a low Reynolds number result, so the flow past the sphere must be laminar. For tiny spheres in viscous liquids, oil drops, dust in air, fog droplets, it works beautifully. For large bodies or fast motion, it breaks down and turbulence appears in the wake. At terminal velocity, the sphere is in equilibrium. Weight, buoyancy, and viscous drag balance each other. Weight is 4/3 pi r cubed rho g. Buoyancy is 4/3 pi r cubed sigma g. Viscous drag is 6 pi eta rv. Setting weight minus buoyancy equal to viscous drag, and solving for v gives v equals 2/9 times r squared times rho minus sigma. All times g divided by eta, where rho is the density of the sphere, sigma is the density of the liquid, eta is the coefficient of viscosity, and g is the acceleration due to gravity. The limiting cases are worth pausing on. If rho is greater than sigma, the sphere falls downward. If rho is less than sigma, the sphere rises upward. An air bubble in water is the familiar example. If sigma is much smaller than rho, we get v equals 2r squared rho g over 9 eta, the limit relevant to a body falling through air. And one elegant scaling. If the radius becomes n times larger, the terminal velocity becomes n squared times larger. Why does the curve rise steeply at first and then flatten? A sphere released from rest accelerates under gravity, but the viscous drag grows with speed. Eventually, drag plus buoyancy exactly balances the weight. Acceleration falls to zero, and the sphere continues at a constant terminal velocity v, t. Stokes' law is not just a textbook formula. Three very different phenomena rely on it. In Millikan's oil drop experiment, tiny charged oil droplets fall under gravity between two plates. Balancing Stokes' drag against gravity and the electric force let Millikan measure the elementary electronic charge E in a parachute. The canopy's huge area produces a huge viscous drag without viscosity. A parachute would be useless. And in cloud formation, tiny water droplets fall so slowly through air that updrafts easily keep them aloft. The r-squared dependence of terminal velocity on radius is exactly why clouds can float. Recall the Reynolds number K equals Vc rho r over eta that decided streamline versus turbulent flow. We can rearrange it to express the critical velocity directly as Vc equals K eta over r rho, where K is the Reynolds number, eta the coefficient of viscosity, r the radius of the capillary tube, and rho the density of the liquid. Reading this carefully, a narrow tube so small r or a viscous liquid so large eta raises the critical velocity, both push the transition to turbulence to higher speeds. A dense liquid so large rho lowers the critical velocity, so turbulence sets in earlier. It is the same Reynolds number physics, just turned around to ask how fast the liquid can go before it turns chaotic. In practice, below Vc the flow is streamlined, Poiseuille's formula applies, Bernoulli's theorem applies, and streamlines are smooth. Above Vc the flow becomes turbulent, Poiseuille's formula no longer holds, Bernoulli still applies locally on average, and energy is lost to eddies. This is why engineers care so much about the Reynolds number. It tells them which equations they are allowed to use. That closes the 3-deck series. Viscosity is internal friction between layers, with coefficient eta equals minus F over A times dV over dx and units Newton-second per square meter. Poiseuille's formula reads Q equals pi p r to the fourth over 8 eta L, with that steep r to the fourth dependence. And series and parallel tubes follow the same rules as electrical resistors. Stokes' law is F equals 6 pi eta RV, and terminal velocity is V equals 2/9 r squared rho minus sigma g over eta, with radius scaling r to nr giving V to n squared V. Critical velocity is V, C equals K eta over r rho, the same Reynolds number physics, written to ask how fast is too fast. The transferable idea across all 3 decks is the same template. Name a regime, write a conservation statement, and end with a force balance identity. That pattern is what hydrodynamics is. Watch for common traps treating the Reynolds number thresholds as universal rather than geometry dependent, forgetting the ideal liquid hypothesis behind Bernoulli, and confusing the volumetric flow rate Q equals pi p r to the fourth over 8 eta L with the linear velocity V of the liquid inside the pipe. Thanks for learning with Viscosity.